Okay. All right. So today, I guess in this video, we are going to be talking about convergence, and we're going to define what we talked about last lecture. What is a Cauchy sequence? So first, we need to define what a sequence is precisely before we can talk about it, right? Because in pure math, it's very important to, precisely define everything you're talking about. So a sequence in a set S is a function which maps from the natural numbers to S, but we denote it as, say, x sub n for each natural number n, right? So the sequence is x sub 1, x sub 2, x sub 3, and so on. So what does it mean for a sequence to converge? A sequence x sub n converges to a limit L means that for all epsilon greater than 0, there is some natural number n such that if little n is bigger than big N, the absolute difference between x sub n and L is less than epsilon. And if you want to write this in terms of metric spaces, because this definition actually works for all metric spaces, you could say the metric of x sub n and L is less than epsilon, or if you want to write it in topological terms, you could say x sub n is in the ball of radius epsilon centered at L. These are equivalent ways of writing this, right? But these are more generalized for metric spaces and metric topologies in general. As a quick example, and you should go through the proof yourself, the sequence of 1 over n converges to 0, and the proof is essentially just the Archimedean property. Now we define what is a Cauchy sequence. A sequence is Cauchy means that for all epsilon greater than 0, there is big N in the natural numbers such that if little m and little n are both greater than or equal to big N, then the distance between x sub n and x sub m, well, I said it backwards than the way I wrote it, but it doesn't matter, is less than epsilon. So in other words, these the distances between the elements in the sequence are getting closer and closer to each other. However, as we noted in the last video, a Cauchy sequence need not converge, right? Just because the elements of the sequence are getting closer and closer together does not mean it's going to converge. However, in the real numbers, every Cauchy sequence does converge. Because that's the completeness axiom. Now, one can prove as a theorem, a convergent sequence is Cauchy. And this is true not just for R, but just in general for an AOF, right? And you want to use the triangle inequality to prove that, right? Because essentially, a convergent sequence means you're getting closer and closer to a specific value, and then to show it's Cauchy, you're just saying that those those values that are getting close to L are going to be close to each other. And so you're going to want to use epsilon over 2, for example. A sequence is bounded a sequence is bounded. That means that there is some real number m such that the absolute values of the sequence are all less than or equal to m. So this is true for all n in the natural numbers. Right? And this is similar to the definition of boundedness that we gave in the previous video, in metric spaces, I should say, rather. You can also show that a Cauchy sequence is bounded. And the proof of this is a little trickier than the last one, so I'll go through in a little bit more detail. The reason why this is that, say, epsilon is equal to 1, for example. It doesn't really matter what epsilon is here. So let n be such that for m and n greater than or equal to n, the distance between x and n is less than 1, right, which is our epsilon. In particular, for n greater than big N, the distance between x sub little n and x sub big N is also less than 1. But the we know that the absolute value of a number is always going to be greater than or equal to the negative of that value, right? Sorry, what am I trying to say here? No, not that, but you can show that this left-hand side, the absolute value of x sub n minus x sub big N, is greater than or equal to the absolute value of x sub n minus the absolute value of x sub big N, which essentially just follows from the triangle inequality, right? Because x sub little n is equal to x sub little n minus x sub big N plus x sub big N, and then you use the triangle inequality here. And then from here, you subtract this to the other side. So what this means is that x sub n is less than 1 plus x sub big N for all n bigger than or equal to big N. Then let big M be the maximum value obtained from the numbers absolute value of x sub 1, absolute value of x sub 2, all the way to absolute value of x sub n minus 1, and then 1 plus absolute value of x sub big N. And the reason why we have to do this is because we basically have to reduce it to a finite set. If you have a finite set, then you can pick out the maximum value. However, in an infinite set, you might not have a maximum value. Therefore, then x sub n, the absolute value of x sub n is less than or equal to m for all n. Because this maximum is going to be the biggest of all of these, and we know that the absolute value of x sub n is bounded by, for n bigger than or equal to n, it's less than this term, and then for each of the n before that, right, you have finitely many of them, it's going to be less than all of these terms. So that concludes the proof. The final thing for this lecture, so this is going to be actually a shorter lecture, is just a little side note. So x sub n converging to L means we say that x sub n is convergent. X sub n is divergent if it is not convergent. However, we will sometimes use the notation that x sub n goes to infinity or minus infinity. What this means, if infinity is a symbol used, I should say, in conjunction with the order such that for all a in the ordered set, which in our case is going to be the real numbers, a is less than infinity. So we're not saying that infinity itself is a number. Instead, we are just saying it is a notational device which says that infinity is sort of going to be bigger than every element in our set. So this notation, x sub n goes to infinity, x sub n is divergent even though we're using this notation. However, not all divergent sets, or sequences, sorry, not all divergent sequences go to infinity. X sub n goes to infinity means for all m bigger than 0, there is a big N in the natural numbers such that x sub n, or I should say such that for n bigger than or equal to n, x sub little n is bigger than m. In other words, you can never pick an upper bound for the sequence, right? It's always, well, that's not even precise. It's saying that if you pick any positive real number, the sequence will eventually stay beyond that number, no matter how big this m is. That's what it means to go to infinity. Similarly, if it goes to negative infinity, you would say essentially the same thing for negative numbers, but instead x sub n would be less than that negative number. So that's just a little side note. That infinity here is a notational device, and so is x sub n goes to infinity. We're using the notation that we use for convergent sequences, but this is not convergent. Right, divergent. It's divergent, which means it's not convergent. And so that is it for this lecture. Do you have any questions? Hello?
Yeah, I'm all clear.
All right, then that's it.